scalar products you can write down. So the two different kinds of structures you can have. Okay, but in a massless theory, it linearizes. And this would actually come up very specifically if you tried to evaluate that diagram on the previous slide. You know, if you actually put this in Mathematica, I think the first way I would probably do it as a student is you'd literally multiply little S matrices everywhere together, and then you'd solve for the on-shell conditions for all the internal lines. Well, when you do that, you'd find that that thing was like 9 loop order or something. There'd be a huge number of solutions. And yet the vertices are telling you exactly which solution you care about at every single vertex. And so just to simplify your life, it would be natural to try to bake this into our formalism, to manifest that this is the solution. You see, this momentum conservation here is a little ambiguous. This is the particular solution of momentum conservation in which all the lambda brackets vanish, all the angle brackets vanish, and this is the particular solution of momentum conservation where all the square brackets vanish. So it's linear in either case. And to make this manifest, you might have invented the Grassmannian. And this is roughly how that story would go, and it shows how general it is. It doesn't have much to do with supersymmetry or the quantum field theory. So the idea is to introduce some auxiliary data to linearize the fact that you have these two different solutions. So I'm going to suggest that for every blue vertex in a diagram and for every white vertex in a diagram, we're going to introduce a little 2x3 matrix and a little 1x3 matrix, B and W. And bear with me because it's not going to look pretty at first, but I promise the structure is beautiful. So that means that if you have this little blue vertex, you're going to write this 2x3 matrix of auxiliary junk, and you're going to, instead of writing this formula, you're going to write this formula. Okay, this does not look simpler at first, but I'll explain all the notation in this in just a moment. And then when we have a white vertex, instead of writing this expression, again, this numerator is whatever it is in theory, in the theory in question. You're going to write a 1x3 matrix W, and you're going to write that expression. All right, the right-hand sides obviously look a little scary, but I hope you notice that there's some sort of structure that's similar between the two. So let me explain the notation, because it's important to really understand what these formulas mean. So first is the volume form on this Grassmannian. So this is the Grassmannian of 2 planes in 3 dimensions, which is how many dimensional? It's 2 times 3 minus 4, 2 squared, because there's a GL2 redundancy, which is 2 degrees of freedom. And how many degrees of freedom are there in G13? Well, they're duals, so you know it's 2, but it's also clear that it's 3 degrees of freedom modulo GL1, which is a 1 redundancy. So they're both 2-dimensional forms. So both, even though I'm writing it in this kind of funny way, I'll explain the notation in a second, these are both 2-dimensional forms. So I'm only introducing 2 auxiliary degrees of freedom per vertex. Okay? And I'll explain what these things are. But now let's just look at the delta functions. Okay, we have this delta function over here. Let's look at the top line. We have a delta function that says that lambda is orthogonal to the orthogonal complement of B. Let me explain the forms concretely. So this notation of divide by vol GL2 means pick a gauge. That means pick 2 of the columns of this matrix to be the identity matrix, and when you do that, you have 2 degrees of freedom left, and then you just evaluate, these things here are the minors of this matrix. So this is the 1, 2 minor, this is the 2, 3 minor, and the 3, 1 minor. And these are the 1 by 1 minors of this 1 by 3 matrix, which is just W1, W2, W3, and I could just write W1, W2, W3, but I want to make the structure more manifest here. Okay, so you can pick this gauge, and then it's this 2 form, or you can pick this gauge, and it's that 2 form. If it's not obvious where this is coming from, notice that if I pick the gauge where minor 1, 2 is the identity, or the columns 1 and 2 are the identity, then in the denominator, 1, 2 is equal to 1. This det becomes 1, and then minor 2, 3 is just B3, 1, and then minor 3, 1 is just B2, 3, and up to a minus sign, that's what you get. So you can pick any gauge you want, the expression is the same. That's why I'm writing it in this more symmetrical kind of way. All right, so let's look at these delta functions. So this one here says that lambda is orthogonal to the orthogonal complement of B. We've seen this before. This means that B contains lambda. Lambda is a 2 by 3 matrix. And if B contains lambda, then they are equivalent as Grassmannians, meaning that so we have 2 delta functions here. Well, on the left-hand side, we had 4 delta functions. Here we have 4 plus 2. So, and we have a 2-form integral to do. So we're going to use these 2 extra delta functions to do this integral to get our left-hand side. And this says that b is equal to lambda. And sure enough, if you replace, so if you do this integral, which is just doing 2 delta functions, you replace b with lambda, and these little minors of b become the minors of lambda. This numerator just becomes a function of lambda, and this delta function becomes momentum conservation, okay? So similarly, you can see here's 2 delta functions on the left, and we have 2 plus 4 delta functions over here. We have momentum. This one's, let's not use those, let's use this one. And this delta function says that w is orthogonal to lambda tilde. W is a 1 plane in 3 dimensions, so 1 vector. And there's a unique, up to GL1, solution to those equations, and that is lambda, w is equal to lambda perp. And if you remember lambda perp, its entries are 2, 3, 3, 1, 1, 2 in that order. I'm writing it in a slightly different order down here. But so the solution here is unique, and it's that matrix that I've written down before. So this is the unique 3 up to rescaling of the unique vector orthogonal to a given 2 plane in 3 dimensions. Okay, it follows from Kramer's rule if you'd like. So I hope I've at least convinced you that the right-hand sides are kind of easy to get from the right to the left-hand side. So it doesn't look like I've introduced too much complexity. But it buys us something incredible, which is that now we have these vertices that are represented with these auxiliary matrices, and momentum conservation here, or rather, which solution to momentum conservation we care about is now linearized here. This is a linear equation in lambda, that's a linear equation in lambda tilde. Now I'm going to claim that given this, we can now generate all on-shell functions in terms of some auxiliary Grassmannian, exactly as we claimed. And it follows from 2 basic rules, and there's a third rule that's kind of useful. The first is if I have 2 on-shell diagrams and I want to multiply them together, the on-shell function 1 and on-shell function 2, you can just take their product, and the answer is the product. What does it mean in terms of these matrices? Well, it's just the direct sum of the matrices, which is like taking the diagonal. And what you see is that if you have a k by n matrix for C1, a k1 by n1 matrix for C1, and k2 by n2 matrix for C2, whatever it is, that you get an element of a big Grassmannian. I'll illustrate this in a second. And this volume form that we get, what happens when you just multiply them together? The volume forms just add. There's a parameter called d here, which is counting how many parameters there are in this form, or how many independent. Actually, let's just not even count independent. Let's just count number of parameters in it. So let me illustrate this. So let's say I want to construct the factorization channel representation inside this Grassmannian thing. The starting point is I'm going to introduce a little 1 by 3 matrix for this one, a little 1 by 3 matrix for this one. And the first thing to do is just multiply them together. And as soon as I multiply them together, I'm going to get a big 3 by 6 matrix. Still, I haven't really glued anything together here, so I haven't really imposed any constraints. And how many parameters are there in the differential form? Well, there's 2 and 2, so there's 4. It's a 4 form in G36. Okay? Now the next step is where all the magic happens, which is, so you have a diagram, you've cut apart all the little vertices, and you just glue them into some giant matrix. And now here's where the magic. Every internal line you have to integrate out, you have to set the momenta to be equal, well, opposite to each other on that. And when you follow, I'll leave this as an exercise. What this does in terms of this representation is it results in a new thing. It eliminates 2 particles, so n goes down by 2. K, how many rows, goes down by 1. And what happens is the 2 columns for the particles that you're going to integrate out, that you're going to set opposite to each other in momenta, those columns disappear, and you project every other column into the orthogonal complement of the sum of the 2. So there's a unique, if this is a k by n matrix, there's a unique k minus 1 dimensional space, which is orthogonal to column A plus column B, and we're going to just project everything into that thing. Now, that a priori doesn't eliminate anything in the form. However, it's obvious that there's a redundancy that gets lost, which is that this geometrical statement that the columns, all the other columns, project into the complement is scale invariant. You can rescale this by anything and the geometry stays the same. So there's obviously a one parameter redundancy inside that. So the number of elements of the differential forms drops by 1. So in practice, what this means is that I'm going to take these 2 columns, and I'm just going to delete them, okay? And this is what I get. So with these 2 fundamental operations, every single on-shell diagram in every single 4-dimensional massless quantum field theory can be written in this way. Kind of trivially, because every 3-particle vertex can be, and then you can obviously glue them all together in a stupid way, and then you can integrate out the internal lines, and you'll get some differential form, which generally depends on the quantum field theory, but this structure is preserved. It's always exactly like this. There. So this is at least the proof that this correspondence between Grassmannian geometry and on-shell functions is generic. There is one more operation which is just so useful, and I've already mentioned it, but I want to recast it in this language that I have to mention it, which is that if you have an on-shell diagram, you can get another one by adding a bridge between A and B, and it's ordered. A is the white vertex and B is the blue vertex. So imagine you started off with some empty on-shell diagram. Again, remember this has a C matrix, which is just the identity in columns, in this case 1 and 3, and zeros in columns 2 and 4. So this is a very kind of stupid, trivial on-shell function that just sets everything to 0. And if you added a bridge between 2 legs, it has the effect of shifting column B by the bridge parameter times column A. So we started off with a function that looked like that. And then so the C matrix looks like that. And then we shift, let's say we add a bridge, we shift column 4 by column 1, we shift column 2 by column 1, we shift column 3 by column, 4 by column 3, etc. And we can keep building up these graphs. So in the planar case, it turns out that every on-shell variety and every on-shell diagram has a move equivalent bridge constructible version. So everything has bridge constructions. That's not true in the non-planar case, and I will show counterexamples. But it still generates a pretty big vocabulary of things, and it's so easy to implement, to start generating up these matrices, that's why I'm mentioning it here. Okay, so there is another way which kind of avoids this whole multiplying little vertices together and gluing them together, because it's, it depends, the resulting expression will depend on the coordinate charts you chose for everything and the order in which you glued things together. The answer will not depend on that, but the form of it will. There's another way, which also has its own redundancies, that's much more direct, called boundary measurements. And this is, in fact, one of the origins of this whole Grassmannian geometry story to begin with, which is that you have some graph. This is a lot more easy to, if I asked you a question, what is the on-shell, or what is the geometry, the C matrix, the parameterized C matrix associated with some diagram, this is the easiest way for you to compute it. It's called boundary measurements. And it works as follows. You first give it what's called a perfect orientation. And a perfect orientation corresponds to you assign arrows to the edges such that every white vertex has 1 in and 2 out, and every blue vertex has 2 in and 1 out. Or said another way, you take a particular helicity amplitude for gluons and you follow it through if you have to assign arrows to an unstructured one. And then you're going to assign weights to every single edge in the graph. You're going to give a weight. And I set a lot of these weights to 1. Everything that's not labeled is 1, and that's with some hindsight. You could assign weights everywhere. I just want an expression I can write down for you. And this is correct. So the C matrix is obtained in the following way, via boundary measurements in the following way. You look at you have K sources. In this case, 4, 5, and 6 are the sources. So you put the identity matrix in columns 4, 5, and 6. Okay? And then the entry of these matrices, so like this entry here, C1, in the 4th position, is a sum of all of a sum over paths of the products of the edge weights along that path. So for example, you look in this thing and you see that 4 goes to 1 via this path, and it's 1 times 1 times 1 times 1 times alpha 5. That's the first term. And then you find another path, this one, it's alpha 8, 1, 1, alpha 5. So you write that entry in. By the way, if there's a closed cycle, you do a Dyson sum. So you replace the infinite sum, the geometric series that you get, with 1 over 1 minus the the product of the things around the loop. So this works fine if you have closed loops. By the way, there's a beautiful theory about how to find all the perfect orientations of a general graph. It's related to Castellan matrices. It's a very nice story, and I'm not going to review it here at all. But for any particular perfect orientation, you just construct this matrix in this kind of simple way. So you go alpha 4 goes to 2, and it's alpha 2. And you keep filling it up. And the volume form for n equals 4 for maximally supersymmetric theory is just the wedge product of all of the variables. So you're done. If you had a non-supersymmetric theory, if you had, say, n equals 0, n equals 4, what you do is you compute something called the adjacency matrix of this graph. The adjacency matrix of this graph is just the weights of all of the pairs of edges between vertices. So it's, so there's an entry alpha 8 in the adjacency matrix that says that it goes from this vertex to that vertex. And it's the determinant of 1 minus the adjacency matrix. This thing has, the eigenvalues of this thing are called the spectrum of the graph. So there's a lot of interesting graph theory to it, and that is the factor. So if you have a perfect orientation and you want to do something in n equals 0, it's that factor to the -4th power in pure Yang-Mills. And this is the only thing that's different from n equals 4 to n equals 0. Yang-Mills is just this little prefactor. And it remains an open question to know. It's an easy, the graph theory of how many perfect orientations there are is very easy to understand, very easily classified. But how many different orientations, or how many different adjacent factors come out of all the various orientations is an open question. Although I wouldn't be terribly surprised if some mathematician somewhere already knows the answer. But that's it. So to get from maximal supersymmetry to non-supersymmetry, you just decorate all of the different adjacent graphs that differ by their spectra. Okay, so I hope I've convinced you now a few different ways that whether we're in planar theories or non-planar theories or supersymmetric or non-supersymmetric, it doesn't matter. It's about the geometry of the 3-particle vertices in massless 4-dimensional quantum field theories. Allows us to write something like this, where the particular representation of the C matrix can come from amalgamating little vertices or can come from boundary measurements, whatever. And this form is absolutely universal. In every single case, you have 2 times k delta functions there and 2 times n minus k delta functions there, which is 2n total delta functions per, so for n external states, there's 2 delta functions each, at 2 times n delta functions. And those always encode, as long as k is greater than 2 and less than n, or greater than or equal to 2 and less than or equal to n minus 2, among these constraints always includes the constraint that lambda is orthogonal to lambda tilde, which is momentum conservation. Okay, so general characteristics. So we have some diagram. What kind of right-hand side are we going to get? We have C is a k by n matrix. N is the number of external legs. K is the number of sources. It's how many rows of the matrix you have after you've collapsed all of the internal lines. This is trivial. It's 2 rows per blue vertex, 1 row per white vertex, and then you eliminate 1 row per internal edge. So that's the number. I put it in trivalent because some people really like to make these bipartite, and I'm not doing that. Well, I haven't done that here. D, the number of coordinates. So what is the dimension of this form? It's a wedge product of a lot of little pieces. How many coordinates survive in this thing? Well, it's 2 coordinates per vertex minus the number of internal edges. So that's how many internal degrees of freedom there are here. And this is also true, but it's true also for bipartite graphs. Again, I'm not going to mention that too much. The number of delta functions. So we have this auxiliary matrix C with all these little auxiliary Grassmannian parameters, alphas or W's or B's or whatever like that. It's a matrix that's parameterized by things, and there's delta functions to lock them into particular values of lambda and lambda tilde. How many delta functions are there? Well, there's always 2n, but that's including overcounting momentum conservation. So if we factor out momentum conservation, that's how many net constraints we have to impose on the C matrix here. Notice that when k equals 2, okay, which is relevant for MHV, these constraints, when you look at this, when k equals 2, this is a 2 by 2 delta function, c dot lambda tilde, and this is a 2 by n minus 2 delta function, which tells you that lambda is equal to c. Okay, so for MHV, regardless of whether we're what diagram we're looking at, if it has k equals 2, k given by this line, then we know that the C matrix is just a stupid way of talking about lambda, the spinors. But more generally, it's not. Now, I want you to note, of course, the dimension of the Grassmannian. So the number of things is n minus k, k times n minus k squared, which is k times n minus k. That is how many independent parameters there are for us to eliminate. And yet, if by gluing together diagrams of arbitrarily large size, D can grow arbitrarily large. So it is obvious that beyond a certain point, if D exceeds the dimension of the Grassmannian, then these coordinates cannot be independent. So we get a degenerate differential form. So certainly, if D is greater than the dimension of the Grassmannian, some of the coordinates must be degenerate. By the way, the dimension of the space C, that of the subspace in the Grassmannian that you are parameterizing by all these little volume forms everywhere glued together, is really easy to compute in Mathematica. You take these matrices, you compute the tangent space, and you just ask for the rank. So if I hand you a random diagram, and I ask, and it has many variables inside of it. In fact, you could label every edge weight to be an edge weight, so you can have tons of redundant variables. And to find out what is the dimension of the space spanned by that set of parameters, all you do is just compute the rank of the tangent space. So it's very easy to do that. And if a diagram has the property that the C matrix that you obtain from the diagram is equal to the number of coordinates, we call it reduced. That is the condition that all of the coordinates in this volume form are independent, and it's a non-degenerate volume form. This is something, I'm emphasizing that this reduction is something that is easy to test in Mathematica for any particular graph. You just compute the boundary measurements, ask the rank of the tangent space. And is it equal to D given by this formula? So the number of reduced diagrams is trivially finite for any fixed n, k, and d. This is a very nice little theorem that we had in the positoroid case by knowing that the number of decorated permutations is a finite list. So we knew that a priori from the fact that these labels couldn't go on forever. But here we have a different way of understanding it that has absolutely nothing to do with planarity. Just that, in the infinite variety of graphs with arbitrarily large number of edges, asymptotically, most of the coordinates have to be degenerate because the dimension is bounded of the Grassmannian. Okay. So I want to tell you basically everything that we know about these non-planar graphs. And the first one is a little different. It's a little unrelated to classification, but it has some really beautiful geometry to it, which is some work from a few years ago with Yaroslav and collaborators Nima, Freddie, and Alex Posnikov, basically characterizing the functions, how to read off the answer from a diagram like this in the case of MHV and in the case where n hat delta equals 0. You'll recall that n hat delta is the 4 times the number of vertices minus 3 times the number of internal edges minus 4 because you're overcounting by overall momentum conservation. Okay, so again, that's graph theoretic. You can calculate that for every one of these diagrams. So for when n hat delta equals 0, we're talking about diagrams that correspond to top dimensional varieties. That means that the dimension of the space that we're spanning inside the Grassmannian is actually 2n minus 4, which is the dimension of the Grassmannian. These are like the Park-Taylor amplitude, okay? Now, a simple exercise that's a little bit more involved than I wish shows that for k equals 2 and n hat delta equals 0, and as long as it's generically non-vanishing, then you must have the following interesting property. There must be n minus 2 blue vertices, and every blue vertex must be connected via chains of white vertices to exactly 3 external edges. And they 3 distinct external edges. If they weren't distinct, then you would have a singularity, or you'd have delta function support. So it wouldn't be a reduced diagram. Okay, so what that just means that on general grounds, if I hand you this is like the leading singularity or the coefficient of a polylog in the MHV amplitude non-planar. To arbitrary order, it's a function like this. So how do we label these functions? One way to do it is to label n-2 triples. So for example, in this diagram, we have this blue vertex has 1, 2, and 3. So we write down the triple 1, 2, 3. This is not ordered, by the way. So it's an ordered untuple, and so is the list of tuples is unordered. So you have 2, 5, 6, you have 3, 4, 6, and you have 4, 5, 1. This is your list of triples. Now let me tell you how to write down the function up to a sign given these triples. Basically, what we know is that C has to be lambda. At least up to GL2, it is equal to lambda. So as elements in the Grassmannian, lambda and C are just the exact same thing. So all of the interesting constraints to talk about are in C perp, which is the orthogonal complement. Remember that C perp dot lambda equals 0. So that's an n-2 by n matrix. And each one of these things basically tells you a little 3-term identity that's satisfied by 2 vectors. And it's those 3 2 vectors. So that means you can just construct this matrix row by row. So 1, 2, 3 tells you that one row of this matrix is that, 2, 3, 3, 1, 1, which is the 3-term identity among lambdas 1, 2, and 3. And then 2, 5, 6 is the 3-term identity among lambdas 2, 5, 6. And you just read off the rows of this matrix. Okay? And what is the answer? That's the answer. It is the product of all of these little each one of the triples gives you a little MHV amplitude, and then another MHV amplitude, and another MHV amplitude, and another one. And each one of these things has a little row, contributes 1 row to C perp. Now, there is one little subtlety that's it's not subtlety, but it's just that this is usually not the way we write on-shell functions, because C star and C perp, so C star might not be, in fact, the orthogonal complement of C is not exactly lambda, it's lambda up to GL2. So there's a little bit of gauge fixing in it, and there's a nice formula for how to do it, or how to compute it, but anyway, that's the Jacobian of the change of variables from C to lambda. So this is a correct expression, it's just not in standard form, because we usually want lambda dot lambda tilde in momentum conservation, not something that's GL2 related to lambda tilde. Anyway, that's the change of variables. So that's how you get the numerator. And now that big, complicated example where I wrote down a formula that looked very much like that, you can just read it right off. And if you don't care about this little Jacobian, it's trivial. All right. Now there's actually something there's another formula for any of these on-shell reduced top-dimensional varieties. Varieties, I just mean a space, a subspace here inside the Grassmannian. Okay. That comes from this intuition from positivity that we'll recall. So recall that Park-Taylor, 1, 2, 3, 4, 5, 6, so ordered, is just the product of all the ordered minors of the lambda. So it's 1, 2, 2, 3, 3, 4, etc. And remember that there was this factor was in one-to-one correspondence with a certain kind of positivity if we viewed the columns as being in RP, or in RP1, which is a circle. So if you take points on a circle in RP1, and you have them ordered clockwise around the graph, then all of the ordered minors of this matrix will be positive. So a factor like this is really in one-to-one correspondence with arrangements of ordered points on a circle. And you can see that the poles correspond to like when 1 collides with 2 or 1 collides with 6, that's that factor and this factor, and etc. We talked about how this encodes the geometry completely. So whenever you see a little Park-Taylor factor, you can secretly think about a geometric constraint, that 3 points are ordered on a circle, or some number of points are ordered on a circle. So take, for example, this one, where I've just labeled the edges, the external particles in some funny way, 1, 3, 2, 4. Okay, it doesn't really matter how we write it. Obviously, this is the tree amplitude involving momentums P1, P3, P2, P4 in that order. So it's misordered relative to the Park-Taylor formula. That's fine. And we can read off these triples pretty quickly, 1, 3, 4, and say 3, 2, 4. And what we find is that 1, 3, 4 corresponds to the geometric constraint that 1, 3, and 4 are cyclically ordered clockwise around the circle. and that 3, 2, 4 are cyclically ordered clockwise around the circle. 3, 2, 4. And if you think about it for just a moment, 1, 3, 4 being ordered and 3, 2, 4 being ordered has exactly one set of consistent configurations, which is 1, 3, 2, 4 all have to be cyclically ordered in that order. And so this pair of triple of weaker constraints, because they're only talking about 3 points at a time, saying that 1, 3, 4 are ordered and 3, 2, 4 are ordered, has a unique configuration, which is that all 4 are cyclically ordered. And so we just write down this triple is equal to Park-Taylor 1, 3, 2, 4. However, I remember I told you that these triples are not actually ordered, and their ordering is not, obviously the ordering hasn't played any role. But the ordering of the triples just played a big role for us, because it had this geometric interpretation. In particular, what prevented me from writing 1, 4, 3? Well, if I write 1, 4, 3, and we say that 1, 4, and 3 are cyclically ordered, and 3, 2, 4 are cyclically ordered, this one satisfies those 2 constraints, and so does this one. 1, 4, 3 are cyclically ordered, and 3, 2, 4 are cyclically ordered. Okay? And you can see that the difference here is the ordering of relative ordering between 1 and 2, it doesn't matter. And so, what's this geometry telling us? Is this the right answer, or is that the right answer? And the answer to that question is they're both the right answer, up to a minus sign, because you flipped one of the things. So this is equal to the sum of those 2, and this is an example of a KK relation, and one of the classes of identities that we have for these kinds of for amplitudes in general, but when you apply it to these Park-Taylor factors. So either formula is valid. It's just that one of them is a little bit more restrictive. And so there's actually a much more efficient, or maybe not efficient, but a more geometrically clear kind of formula, which also tells you that there aren't any double poles, or that it's a sum of every single on-shell function for MHV that is reduced and top-dimensional, can be written as a positive sum of Park-Taylor amplitudes, where the positive sum is given by all Park-Taylor amplitudes such that the ordering of the legs here, 1 through n, are consistent with the cyclic ordering of every triple. And this is gives you alternatives. So instead of for the 6-point example that we had here, do we have any repeated denominators? I'm not sure. But it's not at all obvious that this expression can be written as a sum of PT 1 through 6, with some permuted labels. And it's probably not a short sum. I think this is like 5 terms or something like that. But anyway, there always is a formula like that, where the answer is a positive sum. And so that tells you immediately that a basis for all of these on-shell functions are just the different non-cyclic permutations of Park-Taylor. That forms a complete basis for all of these differential forms. Geometrically, this corresponds to the fact that the positive Grassmannian, or the real Grassmannian, is tiled by the positive parts with all of the n minus 1 factorial over 2 different cyclic patches. Okay, this actually allows you to write down nice geometric interpretations of, say, the KK reductions, which is this thing here. You can flip 1 triple in this thing, which is it's an ordered list. So PT 1 through n is equal to minus the sum of everything over here, which is the set of all of the n cyclic things that are consistent with this list over here. And similarly, you can see the KK, that was U1 decoupling, this one's KK, and you can understand that geometrically here, which is a nice kind of picture for things. But one thing that's missing from this, which is, I'm not even sure how interesting it is, but it's not at all clear to us, or clear at this stage, how many different on-shell diagrams are there? Meaning, I do know that a basis for all of these functions is this, the Park-Taylor factors. Any diagram can be expanded into the sum of Park-Taylors, the positive sum of Park-Taylor even. But I don't know how many different diagrams there are, like how many different sums are relevant for it. I know the dimension of the space, but I don't really know how many different ones. I know how many independent ones there are, but I don't know the number. Beyond k equals 2, you could, in principle, try to answer this question of like, how many different on-shell diagrams are there? How many different geometries are there? How many different functions, how many leading singularities do you need to know to talk about non-planar, say, 6-point NMHV amplitudes, say? And roughly speaking, well, the first idea is much harder than it seems, which is basically, for beyond k equals 2, it's relatively straightforward to construct all reduced graphs. So all possible on-shell diagrams, you can just throw them into the computer. Just compute them all, and why don't you just ask how many different ones, how many different geometries show up? That's roughly speaking the idea. This hasn't been pushed very far, in part because it's much harder than you might think. The first point is that if we're not talking about leading singularities, if we're talking about leading singularities, you can ask whether two things are the same, right? Because these different varieties come in coordinate charts that are generated by some screwy way that you're doing internally about gluing stuff together or taking boundary measurements. So how do you even distinguish between the exact same geometry just constructed in different ways? How do you compare the coordinate charts? Well, for the case of leading singularities, you can just evaluate them as functions of lambda and lambda tilde and see what the answer is. And then you can just check whether two functions of lambdas and lambda tildes are the same. But if I want to answer this more broadly for cases that are not leading singularities, not on-shell, not functions exclusively of external data, but also functions of the internal coordinates or maybe delta function constraints, the problem is that we can't just evaluate them and check that they're the same. So merely computing them or solving the delta functions in terms of lambda, lambda tilde will still leave some undetermined parameters. And how do you know that these things aren't just diffeomorphisms of each other or not? So that's the problem. And although it's, so this is another way of saying it. Although the map, if I hand you any diagram, you can hand me a coordinate chart for a variety, that's very easy to do, the map introduces very specific coordinates that is peculiar to how you solve this. And it's not at all unique. And you and I might generate different coordinates, and it can just be a mess to figure out whether they're the same. They are diffeomorphic. That's a theorem. But whether or not they are, how to realize that is hard. So it can be very difficult to construct or identify diffeomorphisms between different coordinate charts. So we have to come up with some sort of more geometric or more intrinsic way of answering the question of how many different things we can find. And this is the basic idea that my collaborators and I proposed. Oh, by the way, there's another fact, which is that if the number of reduced diagrams is incredibly large, at 6 for k equals 3 and n equals 6, for 6-particle NMHV, I think it starts off, this is already with a lot of very clever culling at the bottom, something like 17 million diagrams that you have to analyze. If you try to do this for 7 particles, it's much bigger. So there's a lot of cleverness in just enumerating all the possibly distinct graphs before you even try to answer the other questions. Okay. So it turns out there is a nice recursive strategy that I think works very well, and it relies on a couple conjectures and some really simple inputs. And then you can throw it on the computer and check. So the first point I've already mentioned, which is that if I hand you a diagram, you can answer the question, is it reduced or not, very quickly. You compute the rank of the tangent space, that's the dimension of the submanifold inside the Grassmannian, you know that. So dim C, easy to compute. D is just graph theoretic. So if these two are equal, that's reduced. You're talking about something I care about. If it's not reduced, you just eliminate edges until it is reduced. Okay. Two varieties are isomorphic if there exists some volume-preserving diffeomorphism between them. That's what we're going to call. Now this is now we get to some conjectures, which are almost certainly true. Actually, I think I might have a fake conjecture on this list, but what I mean by all well tested means that they're theorems for the planar case, and there's no violations anywhere else. So two varieties are isomorphic if and only if their diagrams are related by square moves or mergers. So these two allowed moves. When you do these moves, the coordinate charts change. Those are called cluster mutations, or the square moves are. And I'm not really talking about cluster coordinates because I don't care about the coordinates too much. I care about this geometry. But it's a theorem in the planar case that if you have two graphs that are the same positoroid, that you can get from one coordinate chart to the other by doing a sequence of moves. This is also true for every example we've checked, every pair of things that we claim are isomorphic in the non-planar case. So remember these moves. Okay, this is also unambiguous. The boundaries of some on-shell variety, so it's the submanifold in the Grassmannian associated with an on-shell diagram, are those associated with diagrams obtained by eliminating an edge, such that when you eliminate that edge, the dimension of the subvariety goes down by 1. Okay. So, or said another way, if you eliminate an edge and the resulting diagram is reduced, then I call it a boundary element. So you start off with a diagram like this for G36. This has k equals 3 and n equals 6. And what the idea is very straightforward. Take this, delete every edge in this graph. For every time you delete any edge in this graph, you ask the question, is the resulting diagram reduced? Remember, reducibility is easy to test. And when you do that, what you find is that of all of the edges in this diagram, only 3 are what we call removable, meaning that only if you remove this one, or this one, do you get a reduced graph. Every other edge drops your dimension by more than 1. So we would say, graphically, that the boundary varieties of this variety are the graphs obtained by deleting one of the removable edges. Okay, in this case, there's only 3 boundary elements, kind of cute. Okay, but this part is very easy to test and compute. Now here is the money conjecture. 2 varieties are it feels like something that you can prove if you think about it a little bit, and then you think about it some more and you realize that it's subtle. But let me just make the claim and tell you why it's powerful. So 2 varieties are isomorphic if and only if their boundaries are isomorphic. Okay, that seems pretty non-controversial. You start deleting edges, and then if you see the exact same list of things, or if they're identical, then obviously they're the same. But then what if they're not identical? What if they're just isomorphic? Well, the good news is that these boundaries eliminate edges of a graph. And one of the nice things is that any graph, if you delete enough edges of any graph, you will eventually find a planar graph, a graph that can be drawn on the plane. And being drawn on the plane means that it represents a positoroid variety with respect to some ordering of the external edges. And positoroid varieties are uniquely characterized by which minors vanish. Okay? So I do know how to test isomorphism at the level of a theorem for any planar graph you hand me. If you hand me a planar graph, I just compute all the minors of the matrix, and if the lists of zeros are the same, those things are isomorphic, full stop. And so this little conjecture becomes recursively extremely powerful. So I don't know how to test whether this graph is isomorphic to some other one. Maybe they're even isomorphic to the same elements in the list. That happens sometimes. So like, how do I even know that these things are all distinct? I don't. But I can take their boundaries, okay? And eventually I will hit boundaries which are planar. And as soon as they are planar, I can test isomorphism quickly. And so the idea here is that you can start off with all the graphs you draw, and then you go down in boundaries until you reach planar lists. And then if 2 lists are identical, meaning if they're identical up to isomorphism, then we claim that the parents are isomorphic. So it becomes a recursive tool for checking isomorphism. You know, if it's non-planar, I don't know. Compute the boundary. Is the boundary non-planar? I don't know. Compute another boundary. Keep going, and you get a list of boundary elements. And keep going until, don't delete duplicates, so you're not canceling, so boundary squared is not equal to 0 in this algorithm. You're just listing all the boundary elements as you go. And then when these things are the same, that tells you that they're identical. So then this is a definition which is not actually as useful as I thought it was at one point in time, which is that we can also think about this list of iterated boundaries. These are covering relations inside the Grassmannian. So for the planar case, remember 1, 2, 3, 4, it has 4 codimension 1 boundaries. It has 10 codimension 2 boundaries. It has, or something like that. Anyway, it has a bunch, and they're all connected. So these are all the 3, this is 1 4-dimensional variety, 4 3-dimensional varieties, a bunch of 2-dimensional varieties, a bunch of 1-dimensional varieties, and a bunch of 0-dimensional varieties. And this graph of the covering relations kind of characterizes any geometry. So for example, I can easily compute this using these definitions for any graph you hand me. I can just write, instead of these kinds of things, I'll draw a representative diagram, and I can just compute them all the way down. And if this graph of boundaries is distinct between two candidates, I know they're distinct. So this is going to allow me to filter between non-isomorphic groups. And then this is just useful because I don't want to actually, I do not want to care very much about the ordering of the external labels. So for example, if you take Park-Taylor and you permute the legs on the outside, I'm going to consider it basically the same thing as Park-Taylor. It's a planar graph with respect to some ordering. The geometry isn't very different. And so I'm going to, for our classification strategy, we have the 17 million diagrams to begin with, and we want to say how many different ones are there. We're going to start, and we're going to say that first, two diagrams are the same if they're equal under permuting the legs. So so we're going to look at the equivalence classes of them. And then for the case of NM6 particle G36, there's another operation which is natural for G36, which is that you can change white and blue vertices everywhere, and that corresponds to swapping lambdas and lambda tildes. And for G36, it's kind of natural to say that two things are the same if they're related by parity. So I'm going to say inequivalent thing. The list of inequivalent things are the list of equivalence classes under permutations of the external edges, legs, and parity, changing all the vertices. And now we can answer this question. How many inequivalent things are there in G36? Okay, this is the answer. We took the 17 million, we did all this filtering, and we found 24 different top-dimensional cells. So there's 24 different equivalence classes of top forms, of 9-dimensional forms inside G36, which is the dimension of G36. The boundaries of these things give you 8-dimensional things, and those 8-dimensional things, remember 2n minus 4 for 6 particles is 8. Those are leading singularities. Those are the things. So I'll get back to that. So the 8-dimensional varieties are the ones that we really care about. Those are the ones that appear as the coefficients of polylogs and whatnot. And their identities among these functions correspond to the boundaries of these 24 parents. Okay, but going back to the list of parents, or these top forms, there are 22 of them that you can construct by sequences of bridges. 2 of them you cannot. And only one of the 22 is planar, obviously. There's only one planar one. So you have this list of things to talk about. Interestingly, there's only 10 equivalence classes of leading singularities. That actually isn't counting multiple solutions, which in a work with one of my students who's here, Yatsi Zhang, we showed, well, I mean, it's actually important to care about cases where there's quadratics or cube root solutions to equations. So this is only counting, say, the sum of all residues or something like that. Anyway, 10 different basic on-shell functions, all of which are bridge constructible. One is planar. This is when you take all of the permutations of all the legs and you take the parity conjugate of every single thing, you find that of all of the 10 times 6 factorial times 2 things, which is a very large number, only 3,000 functions are distinct. So there are actually a lot of equivalences between them. And the relations that are satisfied by them, it is spanned by 434 of them. So actually only 3 equivalence classes are needed to generate all of them. So what are these numbers here? As I'm sure you know from Lance's lectures, when we talk about 6-particle NMHV amplitudes in the planar limit, we are talking about the bootstrap program is computing the coefficients of particular superfunctions, like R invariant A minus R invariant B or plus, depending. But there are 6 superfunctions in the planar case, and they satisfy one relation. It's exactly this. It's the identity that we talked about last time, as you can write the 6-particle tree amplitude as either 1 plus 3 plus 5 or 2 plus 4 plus 6. So there's one relation among 6 objects. There's 5 independent things, 5 independent coefficients you need to compute. What this is saying is that at any loop order in non-planar n equals 4, you need 434 of those things. Okay, 434 sounds, maybe it sounds like a big number, but it's a lot smaller than 10 times 6 factorial times 2. So it's not that terrible. And in fact, you only need 3 different seeds of them. So that's pretty good. You keep going, you find 7 equivalence classes of 7-dimensional varieties. There are 3 of which are planar, 5 planar, of the 6 at 6 dimensions, etc. And we enumerated all of this in a paper. And I just want to show you what these things look like, and that'll basically be the end of this. I just want to briefly show you what they look like. So the first claim is that each one of these things, we gave closed formulas for all of these different top dimensional forms. So there's 24 pictures. All but this one and this one are obviously constructed by bridges. They all actually have the same base too, by the way. Notice the base is the constant across all 22 of these. It's kind of nice. So you start off with some 6-dimensional cell and you take 3 bridges in different orderings, and that generates the entire list. Except this one, where you have to glue legs A and A prime together, or this one, which, again, you glue legs A and A prime together. Which is another, anyway, it's also a nice theorem that if you cut things enough, eventually it's bridge constructible. Okay. So what about these leading singularities? So we have the function that we know from our previous lectures. This is the seed in which you write down the 6-particle NMHV amplitude. Remember this expression here, you might remember that, this C matrix, and then these factors in the denominators are just the products of the minors of this matrix that are not 0. So 2, 3, 4 is that factor, etc. So this is how you read off these formulas. And this is the term that you need to write the NMHV amplitude in planar supersymmetric theory. Okay, what about the non-planar ones? It turns out the C matrix is the same, but the function is different, has different singularities. F3 looks like that. F4 looks like that. F9. When we get up 8 and higher, this is actually it's a quadratic constraint, and this one actually appears at 2 loops for 6 particles. And it turns out, just like at 1 loop for 8 particles, you need to care about the 2 solutions to the box cut. In this case, you do need to care about both solutions to these. So there's 2 C stars that satisfy these delta constraints, and they differ by the square root of something. Anyway, this made an appearance in our paper where we wrote down the 2-loop amplitude. We have F9 is also quadratic. This one is actually degree 3. There are cube roots inside this one. And I'm guessing it's not going to appear until 3 loops. But that's an unrelated question. The point is that if you want to go to all loop orders, you need all of this information. These are the functions that you see at all loops, just with permuted labels and maybe parity conjugates. All right, so I want to end this lecture, this lecture series where we started, which is this general correspondence between on-shell functions that we care about, that are interesting, that we care about for constructing amplitudes, we care about intrinsically because they capture quantum field theories non-redundantly, and so they played a huge role in a lot of the developments in amplitudes. And this geometry where every single on-shell diagram corresponds to some submanifold, and we saw today how to generate this manifold. And we have infinite dimensional symmetries associated with diffeomorphisms. And yet, outside of the extremely limited class of planar theories with maximum supersymmetry, we do not know the answers to any of these questions. And most of these can be answered to some extent, like I showed you, by brute force, by just drawing all the graphs and saying how many things are there. What are the relations? These are questions you can answer by direct computation. And it's yet another example of it's a place where it was conceivable that the mathematicians would have already answered all of these questions for us, and then we just need to find out which mathematician to ask and figure it out, as was the case in the planar theory. But absent that, you can either have a great insight that will just answer it in general, or you can generate a lot of examples and study them. And I suspect that if some of you do that, you will find some patterns that are important to answering these questions. And it's a good project because you will be answering questions that have manifest importance for physics, but that are open problems in mathematics. So it's fun to be at the ground floor of something that's still so underdeveloped. So with that, I will end. Thank you very much.
Thank you. Questions for Jake? Yeah, so I guess I'm just not exactly clear where the cluster story came in, since it was in the title.
Yeah.
Yeah, could you elaborate on that? And also, if I remember correctly, the cluster varieties that appear in n equals 4 always close, they're finite?
They do not, no.
They do not. Oh, okay.
Yeah.
Okay.
So-
So okay, never mind. That my second question doesn't
So-
matter then.
At least for this talk, I was mostly interested in the geometry, which is coordinate independent. But for many related, for example, clusters have played a huge role in our understanding of these polylogarithms and the kinds of arguments that appear. So there are plenty of good reasons to care a lot about coordinates. And even though I never emphasize this in this lecture series, the square move, if you look at the coordinate chart that you get, say the boundary measurements for a graph, and you do a square move, and you keep the edge labels the same, and you compute the boundary measurements, that the resulting matrix is not identical. It is related by a diffeomorphism that is called a cluster mutation. And cluster mutations have a rich mathematical story, and there's a lot of interest in it for purely mathematical, and also, I mean, there are plenty of reasons why you might care about coordinate charts generated from other coordinate charts via cluster mutations. And the question of whether or not they close is the question is, if you have a graph and you start doing moves, you generate new coordinates, new coordinates, new coordinates, and in some cases, like for G26 or G46, you find that the list of cluster coordinates is closed under cluster mutations, which is very nice because those happen to be the same arguments that we tend to see in pretty expressions for 6-particle amplitudes. As soon as you get to G48 or higher, so when you have 8 particles or more, this is no longer the case. It doesn't close anymore. And it's interesting. It's worth pointing out, by the way. There is actually one more diffeomorphism, which is not. If you only did the square move, it would close, because if you did square moves forever, you would always just generate planar graphs, and the space there is finite. The problem is that there are non-planar moves that you can do. It's like, in addition to the box move, there's also a hexagon move that you can do that takes a graph from planar to non-planar, and it can start generating complicated graphs. So anyway, there's plenty of, if you look at, this is why people say that the cluster variety, as cluster varieties, not all of them are finite. Anyway, I'm not sure, I didn't have time to talk about the coordinates in particular. So I don't really care about the sequence of how many different coordinate charts there are, which is a cluster question, or even how they're related to each other. I just want to know about the geometry. But because the square move is the cluster move, as the cluster mutation, all of these things have a cluster algebra attached to them. So that's why I'm calling, I guess it's a buzzword that I didn't even mention, but in the talk. But what I'm calling on-shell varieties are just intrinsically the subspaces associated with on-shell diagrams. These are all actually also cluster varieties, so are of interest independently to mathematicians.
Yeah. Thanks a lot for the lectures, Jake. I wanted to ask something that I think came up in a previous lecture. You showed some formula for leading singularities beyond n equals 4 supersignals.
Yeah.
And there was some factor to the power n minus 4.
Mm-hmm.
I was just wondering to what extent this has been developed, for example, in the Grassmannian formalism, and or if not, if you can say something about the difficulties there, or what the current status is.
This is the kind of question that I would bet above even odds that there exists a mathematician somewhere who knows the answer to how many n equals 4, or sorry, how many prefactors there are. But I have not found that mathematician. I do not know the answer. So what I know is from just brute force things, like you look at 4 particles or 6 particles or something, and so there is a beautiful mathematical literature on orienting these graphs. And there's a lot of powerful tools there. And there's also a beautiful mathematical literature on the spectra of these graphs. But it doesn't seem like anybody's ever cared to answer the question, how many different determinants of 1 minus the j, how many different prefactors are there for a given graph? So it's something you can just, because the perfect orientations is something that's very easy is well understood, you can just throw it on the computer and brute force answer it. But I've done that a few times for low levels and not been able to identify patterns. But I still think somebody could just, I'm going to tell the story to somebody, a graph theorist someday, and they're just going to know the answer. I just haven't been able to Google it yet. Yeah.
Okay, any more questions? If not, thanks Jake again for the whole lecture series. And we go for lunch and reconvene at 3.